Hi everybody, my name is Charles Feddersen. I'm the Group Product Manager for PostgreSQL Hyperscale Citus in Azure, which is a service for building distributed applications on Postgres. In this session, we'll provide a technical overview of the service and then break into a demo to show you how the distributed architecture for Postgres works and some examples for building distributed applications. Let's get started. So the agenda for this session, we'll start with effectively a detailed technical overview of the service. We'll talk a little bit about the architecture of the service. Again, Hyperscale Citus is a distributed Postgres platform built using the open source Citus extension. And so we'll take a look at what that means in the context of this service. We'll highlight some of the key features within the managed service and then talk about how you can model data at scale. We'll interleave a couple of demos in here. The first demo up front will be just a basic one about how to create distributed data across a cluster. And then the second demo will get more into a specific end-to-end scenario for building a multi-tenant SaaS application, which is one of the really common applications that we see being built on the distributed database system. And then we'll wrap up everything at the end, as usual, and just conclude the topics that we talked about. So let's start with the overview. So as I mentioned, Hyperscale Citus is distributed Postgres. And what that means is that it's effectively Postgres, the open source version of Postgres, running on a collection of nodes, we call them worker nodes, within a cluster, with a distributed query engine, which is what we call Citus, that sits on top of them. And it enables you to write applications against a single endpoint. So treat the database as if it is just a single Postgres server with a single connection string of servers and logins and what have you. But when your applications are submitted to the endpoint, Citus, the distributed query engine, determines how to execute that query across the cluster of nodes. Now, the two typical ways that can happen is that the query gets routed for execution on one of the nodes because it's determined that's where the data lives, and we'll show that a little later in the multi-tenant SaaS demo as well. Or it could be a fan-out query. Imagine a more analytical type query where you're doing a broad count, group by sum across the table. Now, of course, in distributed systems, the intent of the system to create the scale is that only a piece of the data of a given table or a given database is stored on each of those nodes. And so when you run a global count group by for a table, it's got to apply that to each of the worker nodes and then run a secondary sum. But the key thing is, from an application standpoint, it feels exactly like Postgres. You just connect to one place. And then we figure out how to scale that query across the cluster. Now, of course, these clusters are elastic. They scale out. The compute nodes themselves can actually scale up and down. And then it's a shared nothing architecture as well, which means that the storage increments with the compute. So your IOPS grow with the compute. And this provides very linear scalability as the application grows. The system itself shares a distributed architecture that may commonly find in distributed data warehouse systems. Things like Synapse, for example, use a common scale-out application. The difference, however, is that Citus and Postgres is deeply optimized for OLTP class workloads. Now, there is a columnar format in the platform as well, which can support HTAP, or effectively blending operational with analytical scenarios, that hybrid transactional analytical processing. But we really don't consider Hyperscale Citus to be a first-class or optimized data warehouse system. It's built and optimized for operational OLTP workloads. It provides the acidic transactional consistency that you would want from a database like that. But we do supplement with some columnar capabilities that you can run some operational analytics directly within the system as well. So how do you go and do this in SQL? So there's two SQL statements here. The first is one that would be very familiar to anyone who's effectively worked on a SQL-based system, and it doesn't matter if it's Microsoft SQL or Postgres or anything else. It's a basic create table statement. Here you can see we're going to create the table sales transactions, and we're going to give it 3 columns: transaction ID, customer ID, and the amount of various types. Really basic stuff. Where Citus comes in is it provides an API through Postgres extension model where you have functions to then convert that table into being a distributed table. And so here you can see I'm taking my sales transactions table and I'm running the create distributed table function. And what it says here is the first parameter is the name of the table, and the second parameter is the column name that I'd like to shard on. Now, the way sharding works, it uses a hashing algorithm which is deterministic, and by default, it will shard that table into 32 shards or 32 separate Postgres tables on the cluster and assign them equally across nodes in the cluster. So imagine that you've started with the create table statement and you've got an 8-node cluster, and then you run create distributed table. What will happen is we'll create 32 shards and we'll effectively place 4 of those shards on each of the worker nodes to create balanced scale across the cluster. So to illustrate that a little better, that first create table sales transaction statement will create a single table, which is what that single red box is. When I run the function, we now go and create 32 shards. Now to the user, if you're in a development environment, whether you're in PSQL Terminal or you're in pgadmin or any other Postgres tool, and actually sort of an interesting thing just to point out here is, given that this is effectively pure Postgres, really the entirety of the Postgres tooling ecosystem works on Hyperscale Citus. It's very uncommon to find anything that doesn't work properly. We'd certainly love to hear if that's the case. What this means is that from the user perspective in the tooling, you still only see one table. You see sales transactions. But under the covers, what we're doing is we're creating 32 shards, which creates this scale out efficiency on a cluster. So imagine a table that's got 32 billion rows, simply for maths purposes. In this model, those 32 billion rows will be in a single table in a single server in the topmost form factor. When we distribute that, we put approximately, depending on the sharding algorithm, about 1 billion rows into each shard and spread that across 8 nodes. And what that enables is far more scalability in the platform and more performant queries. And we'll talk about the performance characteristics shortly. So if I build upon this and how the hashing algorithm works, the hashing algorithm is deterministic, which means that in the situation where I've hashed on my customer ID, which was the first column in my table, so it's represented by the first value in the values section of my query below, value 1, customer ID 1, will always be located to shard, in this instance 2. And I've tried to color code the blue query to which shard that would land on. The second statement, insert into sales transactions value 2, will be located maybe on shard 5. I don't really know, but the chances are it's going to land on a different query. It may actually land on shard 2 as well, but it's unlikely. And so obviously now when you get past 32 values, these will appear on this, these will materialize onto repetitive shards, but for all intents and purposes, it's pretty balanced. But the point that I'm really trying to make, and the point that I made earlier, is if you don't have a distributed table, we will always put values into that same singular table, which is where you can see the blue and the green above. Now, if we take that one step further and think about how this applies to the cluster, I mentioned earlier, imagine you had 8 nodes. This demo here actually is really talking more about 16 nodes. So I've got 32 shards, we're equally balanced. So in that case, we're going to put 2 shards onto each node. But here, now so you can see I've got one row that I've put onto node 1 and one row that I've put onto node 3. And as I continue to add rows, we'll continue to balance those across the shards. But the key thing to note here is that already I've been able to distribute my database across 2 physical nodes in Azure, which is giving me this scalability uplift versus running it on a single node had I been running on traditional Postgres using sales transactions. So let's flip over to a quick demo now and show you exactly how that looks like in Postgres and describe to you how we create these distributed tables. Okay, so in this demo, we'll walk through a very simple scenario of creating both a distributed and a reference table. So I'll start by going ahead and just clearing out any tables that I've got in the system here. I'm using pgadmin, and so you can see there are a couple of tables that didn't exist, so that looks good. So let's start by having a look at what we've got now in the database. And I'm going to start by using PG tables, which can show me what I have in my database, and I have nothing, as you can see. And then in Citus, we have this separate Citus view where we can see the tables that have been distributed or created as reference tables in Citus. And as you would imagine, with no tables, there's nothing there as well. Okay, so now let's go ahead and create a table. This is going to be a vanilla Postgres table. We've got some basic types here, integers and varchars. We're giving it a primary key where it's a composite key on tenant ID and customer ID. So we'll go ahead and run this. Table's created. Now I haven't done anything special for Citus though. And so if I run my PG table statement again, here you can see I've now got customer. So that's the table I just created. But if I take a look at Citus tables, you'll see that there's still nothing here. And that's because I haven't done anything specific to Citus. So my next command here is going to create a distributed table. And I'm going to pass into it the name of the table and the column that I want to distribute on. And so this is a function within Citus. And I chose customer ID, which if I scroll back up, you'll recall I have a customer ID column here. There's a whole set of guidance on how you should choose the distribution column. It's a really simple thing. Really, typically you're looking for columns of high cardinality, common joins, and where you're filtering as well often, which creates more scale. There's a lot in the docs that you can read up on here, but it's pretty simple concept. So I'll go and create a distributed table now. And so to show how that's moved forward, let's again go and take a look at PG tables. And we'll go, as we had, a customer table. But now if we look at Citus tables, you're going to see that there's a record here where this was previously empty. My table name, customer, is distributed, and the distribution column is customer ID. So now I can go and insert a few values here. The tenant ID, the customer ID, first name and last name. So let's go run that. And what you'll see now is that I can run two different types of query. One is going to be what we call a fan out query, where I can take a count star of all of the records. 3, simply, obviously, because I just put in 3 records. Or I can run a count star where the customer ID equals 1. And the key to this part of the demo is that this is the distribution key. And so I'm going to go run this, and it's 2, of course, the top 2 records here. But what I really want to do is show you the explain statements. Because I have a distributed table now, what you can see here is that I had a task count of 32. When I created the distributed table, it actually created 32 tables under the covers on my cluster. And that's why when I went to count all of the records in the table, it actually sent down 32 separate count stars that it subsequently runs in parallel across the cluster on each table, and then sums them up again. And that's how you can get a tremendous amount of scale from distributed tables, because we're fanning out the query. Now, remember here that I distributed my table on customer ID. That means that all customers with value 1 or other values, but definitely I know value 1, are going to be stored in the same shard. And Citus is smart because it knows that, it understands the deterministic behavior and the guarantees that the sharding algorithm provides. If I run this, you'll see that my task count is 1. We know, or Citus knows, that there are 31 shards that will never have customer ID, any row where the customer ID is 1, because the sharding algorithm guarantees to put them in one place. And so this is where you can get tremendous scalability in the system, where filtering on the sharding column enables you to operate on only one worker node and one shard. And you can imagine that as you get to larger clusters, 4, 8, 16, 20, 24 nodes, the ability to actually ask the majority of the cluster to do no work for a given query, because it knows all of the data it needs is attached to one node, creates a ton of scalability. Now, there's another capability in Citus where we can look at the actual shards themselves. So if I go run this query, what you'll see here is that we get 32 rows back. And remember, we had 32 shards when we ran this query here. And so all this is really doing, if I just scroll this up a little bit, is showing me all 32 shards or tables that are under the covers. And so the first 16 here are on worker node 0, W0, and then worker node 1 has the other. What you'll also notice is that some of them have got data size. And so what this means is that of those 3 rows that I put into the table, 2 of them have probably gone to one of these, and 1 of them has gone to the other. But we don't really know where they are at this stage, but we can actually find out. So let's take a look here. I've got 2 shards with data in them, 103.175 and 103.152. Imagine we actually wanted to know where customer ID 1 is. We can run this function here, and it's going to return one of these values, either 175 or 152. So I'm going to run that. It's 152. So what that means is that those 2 values that I inserted, 11 and customer ID, so this one in here, Fred and Bill, have both been put into that shard 103.152. And so you can understand where this data is being stored. So let's go clean that up again. That's a distributed table, and now switch to a replicate table. So I drop this. Let's just prove again that everything's gone. Yep, no table, and if we've got no table, we'll obviously have no Citus table. I'll create the same customer table again. So that was distributed tables before, that was fanning a table out across a cluster, but often for smaller tables, what we want to do is create reference tables. And a reference table creates effectively a mirror image of every table locally on each node. And that enables tremendous scalability when we're joining between tables, because we can co-locate the entirety of a join on one node, and we don't need to shuffle data necessarily between the nodes. So we recreated customer. I can hit run on this one. Yep, and I can hit run on this one. We haven't done anything, so that's going to be empty. So let's now run the function to create a reference table. So we'll go and do that. We'll skip ahead to save some time here and look at Citus tables. Now it's reference instead of distributed. Because it's reference and it's replicated, there is no distribution column. So that's why that shows null. And now if I show you this to look at the shards, we had those 32 rows for the distributed table before, but now as a reference table, we've just got a version on the coordinator and 1 version each on the workers. And I can go ahead and insert some values into here, the same values that we did before, into my reference table. And if we look again, you'll see that instead of putting it on one of the rows, it's put the data everywhere. And that's the behavior we expect on a reference table. So in summary, what this demo showed is the basics of how to use the Citus extension to create distributed and reference tables. But note that we started in all instances with just vanilla Postgres tables and then layer the Citus capabilities on top to provide the scalability of the data across a cluster form factor while still maintaining all of that Postgres compatibility. Okay, so let's keep moving. So it's important to understand why we use distributed databases for applications and the actual benefits that they provide for different classes of operational application. And this is a really simple chart that explains it. It was actually published in a white paper that we authored for the SIGMOD conference for Citus in 2021. Databases tend to have this interesting characteristic where performance can fall off a cliff when they reach a certain threshold. And that's typically where the cache utilization starts to drop, right? Databases are exceptionally good at caching data locally in memory to dramatically reduce the latency of accessing that data to resolve queries. The problem becomes is that when a sufficiently large amount of data is constantly being accessed for the workload that's being run, and that exceeds the available memory in the system, then the IOPS start to increase dramatically and latency creeps into the system. And so what you can see in this chart is that on the left-hand side, running effectively a single node Postgres with a given relatively demanding workload, you can see that we were able to process about almost 16,000 orders per minute, exactly 15,923. But the latency was quite high. The latency actually got up to 368 milliseconds. Now, when we scaled that to a 4-node Postgres Hyperscale, of course, there's more capacity and more compute there, but we were able to increase that up to just over 214,000 orders per second and reduce that latency to 39 milliseconds, which is an end user who, as an end user who's waiting for an application to respond, that will be a dramatically better experience. Now, what's interesting about this, if you look at the text on the right, is the characteristics of performance versus cost. When you move to a cluster-based form factor, you actually go 5x cost versus 4x. It's about 5x. It's actually a little less, to be honest, because what happens is you introduce a coordinator node, which is typically a little smaller. Sometimes it can be bigger. I mean, you can choose the size of the coordinator, but for simplicity, it's 5. You increase the cost 5-fold because you move from one server to 4 worker nodes and a coordinator. Yet we're able to increase the throughput of the application by 13x. Now that's a great return. That's a better than linear improvement on the performance of the platform, performance of the workload relative to the cost. And that's because when this workload crossed a certain threshold, the IOPS and the latency creep into it, where you're getting a reduced cache hit latency for the OLTP application. You're churning your disks more and more. And so the latency goes up and the throughput drops. When we add more resource, and fundamentally we're adding more memory, we're able to keep all of that required data locally in memory in the caches. And so the latency plummets, and therefore on an orders per minute measurement, we can process significantly more of them. And so being able to scale out an application to a cluster, as I mentioned, can yield tremendous scalability improvements, not just actually in par with the incremental cost, but in this case, dramatically better improvement in the platform than the cost that we actually incurred by moving to more resources. So I just want to take a moment to talk about what we're actually building on here as well. In Hyperscale Citus, we use community open source Postgres. And that means that the Postgres engine we're running on the worker node is fundamentally open source, and it's the exact same version that the open source community or the Postgres community releases. For distributed query execution, we're using the Citus extension. The Citus extension is also an open source technology that you can download and actually install yourself on your laptop or server or what have you. And so although we enrich these capabilities tremendously in the managed service and provide a ton of elasticity, high availability, rapid in security capabilities within Azure, if you'd like to get started or even run your workloads, potentially even production on open source technology, you can take effectively these same 2 components that we're using, the core Postgres engine and the distributed engine called Citus, and you can run them locally on premise as well. Now, why is it important that we use the open source Postgres version? Because we use open source Postgres, we're able to actually ship the latest innovations from the Postgres community within 1 day of that major release dropping. And this is something that we did in calendar year 2021 with Postgres 14. And although we're not there yet, it's our intent to go and do the same thing when Postgres 15 lands, presumably in late September or early October this year. You can see on the right-hand side, we published a blog last year that described what we had to do in our engineering systems to be able to achieve this. But we believe it's important because it enables developers to benefit from the latest innovations that are coming into Postgres, but benefit from them in the managed service as a distributed platform within 1 day of the community dropping them. In other formats, you can see version lag come in to Postgres, but in Hyperscale Citus, like I mentioned, 1 day after the community drops it, those features are in, and you can start to benefit and build on them in your application. Now, we don't expect you to build on them in production immediately, but to start prototyping some of those new capabilities and see how you could apply them to your applications, they will be there in the managed service. You don't need to get started on open source Postgres and then wait for us to get to the managed service. It's our goal to deliver that day 1 after availability every year. The other thing that comes with building on true open source Postgres is that we inherently get the benefit of a variety of extensions that are available in the Postgres community. Now, I'm not going to walk through every single one of these. It's a bit of an eye chart. But some of the very common ones that come up are things like PostGIS and the ability to do geospatial work in Postgres, which is very, very powerful. Things like HLL up in the data type section for hyperlog approximate distinct counts in data. Things like PGPartman is frequently used, and others here as well. We know these extensions are frequently used and embraced by developers to enrich their applications in Postgres, and all of these are available in Hyperscale Citus today. And so for scenarios as well where perhaps, if you think back to what I just talked about with starting on Postgres and then scaling that application out, there will be many scenarios where you are running on a variant or an architecture of Postgres that is single node today, and you see the value in scaling that out for that reduced latency, increased throughput that I described on that chart. What's important when you do that is you've got the compatibility to bring forward the extensions that you're using in that existing Postgres application as well. It doesn't really work if you want to move to a distributed system, but the extensions aren't there. That creates a whole bunch of refactoring if you can actually replace the functionality at all. And so having these extensions in Citus we think is really valuable for customers. And again, it's one of the great benefits that we naturally inherit from building on true native Postgres, or as we often term it, just running Postgres at the core of the service. One of the other great benefits that we've built into the system is the ability to scale the platform online. The demands of applications are constantly changing. Applications are growing. We're accumulating more data. We may be bringing more users to the data. And so whether it's an increase in users or an increase in data or both, ultimately an application that started maybe on a single node or two node form factor will need to scale out to 3 nodes, 4 nodes, 5 nodes to continue to deliver the performance and throughput characteristics. With Hyperscale Citus, we support online scaling. Now it's actually a 2-step process. First of all, you scale the compute and then you scale the data using another one of the Citus functions in the platform. But it means that you can scale your application completely online without any interruption to the application that's in production. And this is important. Operational systems in particular tend to run around the clock. They're more busy at some times of the day than others, of course, but they're always up. And so the ability to scale online, we believe, is critical. And so the online scaling here enables you to add nodes to the cluster, rebalance your data across the nodes without any interruption to the application. And that, of course, looks something like this. One of the other key features within Citus Hyperscale is the ability to effectively rebalance the workload across shards. And this typically manifests in 2 different scenarios. The first is that you've added nodes to the cluster and you need to then subsequently rebalance the data across the nodes to try and equally distribute the shards across the cluster. And so imagine that you started from, say, a 4-node cluster with 8 shards each, as we just showed in the demo earlier, that default of 32 shards per node. So by default, creating a distributed table on a 4-node cluster will attach 8 shards to each. But then you scale the cluster to, say, 8 nodes. You'd run a function within Citus to rebalance that, where it will subsequently assign 4 shards to each of the 8 nodes to try to balance that workload across the distributed system. One of the key design principles to any distributed system is you want to try and balance the amount of work happening on each node to the limit possible. Otherwise, hotspots can occur. One node can run a little hot and potentially impede the throughput of the entire system. The other scenario is where over time, as workloads mature and data is loaded into the system, skew or imbalance can start to occur within the platform. And so in scenarios such as that, a rebalancing strategy may actually be to move a larger tenant to a less utilized worker, or a larger shard, I should say, to a less utilized worker, and then subsequently perhaps move a shard from a lower utilized worker to a different worker. And as you can see here with the animation, we did a simple swap where the orange worker node, node 4, had two disproportionately large shards, which may have just been how data accumulated over time. If you think back to our customer table example before, maybe we had a customer with sales transactions who just bought a lot more items. And so they were just creating a lot more data on a given shard. And so in this scenario, we switched them around to try and balance the total amount of data and the total amount of work that's occurring on each worker node. And so Citus provides, or Hyperscale Citus provides, two approaches to doing this. Notably that it can be online or an offline shard balance. And like I said, there are two key scenarios: changing the size of the cluster or changing workload dynamics of your application, perhaps without actually changing the size of the cluster. When developing enterprise applications, obviously high availability is critical. And so Hyperscale Citus also provides out of the box high availability capabilities where the RPO is 0, the recovery point objective is 0, which basically means synchronous replication. And so in this scenario, if a node in the primary cluster goes down, will automatically fail over to the secondary with 0 data loss, and obviously with no application changes required either. It all still sits under the connection string. But the secondary node will now pick up the work while the primary node is recovered. And so this is available by default. High availability is disabled. You can enable it when you're provisioning, or subsequently post-provisioning you can turn on high availability as well. It'll take a little bit of time to effectively seed the replica to bring it up to speed with the primary, and then after that synchronous replication continues between the primary and secondary and will automatically fail over, as I mentioned. And this is actually what enables us to deliver the SLA that we commit to for the managed service as well. There is also a mechanism for asynchronous replication as well, but this is not so much targeted at high availability scenarios, at least not within region. It's more targeted at scalable scenarios. Imagine applications, perhaps the most notable exception of a read-intensive workload is things like social networks or those web-based applications where the vast amount of traffic is going to be reading from the database. And those reads don't necessarily demand up to the second consistency with respect to the changes that are being made. You imagine that someone in a social network changes their status, for example. You may not see that status immediately. It's okay to only see that update a minute or so ahead of time. So with read replicas in region, what we enable you to do is create readable secondaries of the primary and connect your application and run select queries against them. And so in this model, there is some basic lag between the primary and the secondary. And the secondary is limited to read only, but it does offload those read intensive workloads from the primary so that they can be focused primarily on inserts, updates, deletes, data modification statements. There's no issue with reading from them as well, of course, but it provides another dimension of scalability. And so if you think and sort of recap to what I said before around the clusters, your Hyperscale Citus can start small, can scale out to multiple nodes as a cluster. Those nodes themselves can scale up actually to 96 vCores at the worker node level. And then you can scale in a third dimension. Beyond scaling out and scaling up, you can then scale to read replicas as well within region for these really data intensive workloads with high read requirements. In public preview at the moment, we also have cross-region read replicas. And this serves really two distinct scenarios. The first is that it provides geo-redundancy in the event of needing to do geo-DR. Now, this is using asynchronous replication as well, so it means that the RPO is greater than 0. And when the primary goes down and you fail over to a secondary in a different region, that will not have up to the last transaction of data. The latency will vary depending on where it was in the replication point. But at the point that the primary comes back up, you'll need to effectively merge that data back together to get back to the latest state. But it does enable you to stay up and continue to serve an application through promotion to a different region. The second is around localized low latency for very performance sensitive apps. So again, a central primary that probably has a relatively low amount of traffic relative to the secondary. But if you've got you're building for your organization with remote offices, you're building SaaS applications where customers are deploying close to the source to read these applications, where the vast majority of the traffic is commonly read, you can reduce that latency into just a few milliseconds to read locally. You'll take a slightly higher latency hit for the write back to the primary, that in this case is on the East Coast in the US. But for the vast majority of application traffic, you're going to be in a good shape, low latency, really interactive experience for customers. So let's switch over to a demo now, and I'll just show what a couple of these things look like in the portal before we wrap up this section and move on to the next demo. So if we jump into the Azure portal now, I can show you just a quick walkthrough of some of the features that I've just described. Let's start with the scaling and high availability. I can click on compute and storage, and here you can see I'm running a standard cluster where my worker node count is 2. To scale that cluster out, similar to how I talked about online scaling and then ultimately shard rebalancing, I simply move the slider and the numbers move. I won't go ahead and scale it right now, but you get a sense for how easy it is to add compute to the cluster. For high availability, we actually bundle that at the bottom of the compute here. So in this server group, I haven't enabled high availability, but by simply toggling this to yes, that will go and provision a highly available secondary cluster. It'll begin the replication process to seed that cluster with data. And then, as I mentioned, it's effectively automated after that with respect to failover of the nodes to keep applications running in case of node failover, or node failure, I should say. With respect to replication, if I come over here and select replication on the left-hand side, let's go on, skip out to that one. You can see I don't have any replicas configured. There's no results here. If I select add replica, I have the option to add a server group here. Just put something in here. And then you can see that I can choose my location. Now, East US 2 is where my primary cluster is. And so if I select this, this will inherently give me an in-region replica for scaling those read workloads in the same region that my primary exists. However, I can also select other regions around the world. And if I go and select one of those, we would say perhaps like West US 3 or something like that, and then I enable this, this will inherently create cross-region read replica where I can connect to my secondary read cluster in West US. And if I've got read workloads there, obviously that latency is going to be dramatically lower than needing to connect to the East Coast of the US. So just a really simple example in the portal around how easy it is to enable these features for scaling, high availability, and those read replicas, both in region and cross region. So you can get a sense of, once you're running, how easy it is to light up some of those capabilities. So let's bring it back into slides now. What I'd like to do now is switching gears from talking about the managed service. Let's go and look at a second demo now. And in this demo, I'm going to really build upon what I showed in the first demo with that single table by showing how we can now incorporate multiple tables into a single solution, distribute them in a manner that makes it very scalable and performant for a distributed cluster application. And then after that, we'll go and wrap the session up and call it a day there. Okay, so let's now make a start on the second demo, and we'll go a little bit more slowly this time and really explain some of the things that are happening here. I think we moved a little quicker through the first demo just because it was a little more simple, but we're going to do some more complex things here. So we'll take our time and I'll just explain it as we go. So let's start by cleaning up again and make sure we don't have any tables present. So this time we're actually going to work with 3 tables. We're going to work with a customer table that we used in the first demo. We're going to use an inventory table, and we're going to use a sales transaction table. And we're going to build effectively a multi-tenant SaaS application. You can think about this type of workload as Perhaps like an ISV is building software on the platform, and they want to create an incredibly efficient utilization of resources by making it multi-tenant, so that when their customers are using it, they're all sharing the same capacity in the same database, the same data model, and everything. So we'll start just by dropping the tables and clearing that out. They don't exist, you can see. So if we take a look at what we've got in Postgres, it's clear, and just like we showed in demo 1, we can also demonstrate or show that there's no tables here for Citus. Okay, so we'll go ahead and create our customer table again. It's got the tenant ID, customer ID. We didn't really talk about the tenant ID too much in the first demo, but you'll start to see a little bit more of that here. So tenant ID and customer ID are both integers. We'll have a first and a last name, and we'll give it a primary key on the tenant ID and the customer ID as well. So we'll go ahead and create that, and then we'll go and distribute it just like we talked about in the previous demo. So select create distributed table function, which is the Citus function, the customer table, and we're going to apply that hashing algorithm to shard the data on customer ID. So if we go run that, then we've got a distributed table. Now, one of the things that we didn't show actually is that you can actually grow the shard count as well. Now, of course, with 32 shards, the largest we could grow a cluster to support that scale is 32 nodes, right? At a minimum, it's got to be 1 shard attached to each node. And if the workload starts to really scale and you need a larger cluster beyond 32 nodes, then you're going to need to actually crack those tables open and split those shards, so to speak, to make smaller chunks that you can then attach to more nodes. And so there's a function for that. It's called alter distributed table, and we pass a table name. We give it the new shard count. Remember, we're on 32 at the moment, and we're going to go to 64. And then cascade to co-located means that if there are other tables co-located on the same shard key with the same shard count, then that would actually push down to other tables and redistribute them out to 64 shards as well. So if we go run this now, this will run. There's just a void response, but we now have 64 shards. So let's now go and create a second table. And so in this scenario, we've got the sales transactions. You think about the relationships here. Customers are buying things, with the purchases that they're making are reflected in sales transactions. And so this table actually has a tenant ID, the customer ID, as we had before, a transaction ID, so that we can keep track of each individual transaction, the inventory ID. So this is like the key or the ID of the item that they're purchasing. Of course, we always want to know the time that the transaction happened, and amount, we're just going to use a basic decimal type. We'll also go and create a primary key on this table, and we're going to use a composite of the tenant, the customer, and the transaction ID. And so if you think about this, of course, that within a tenant, there will be multiple customers, and then with each customer is going to have multiple transactions. But that transaction ID technically is probably going to be ever ascending with respect to the individual tenant, but putting a customer ID in there, I guess, gives us just a little bit of peace of mind that these three will always be unique. Really, it depends on how you design the app. So let's go and create that table as well. And let's stop and check our system catalogs here. So we've got 2 tables now, customer and sales transaction, the owners, as you can see. You'll notice here that the Boolean is true and false. It's true where, has triggers as Boolean. It's true where we've distributed the table, and it's false where sales transaction. Just a small detail, but you might notice that. So let's go ahead now and distribute sales transactions. We'll take a key, so we'll take tenant ID. I'm choosing tenant ID somewhat intentionally for the purposes of the demonstration, and I'll show you what we're going to do with that shortly. But remembering that as I select tenant ID here for the sales transaction distribution key, keep in mind that I used customer ID up here for customer, and I'll show you why that's important in a second. So we'll go ahead and run this, and this will distribute that table as well. We'll go run our alter table and put that into 64 shards also, no problem. Now let's go and apply a foreign key. And so I want to alter the, remember my customer ID, my customer table is going to have the unique record for each customer. So that's effectively going to be, so the primary here, and we'll foreign key down to sales transactions. So we're going to alter the table sales transactions. We're going to add a constraint, and I've just given it a name, foreign key underscore transaction ID underscore customer ID. These will be the columns that we foreign key on, and we're referencing upstream the customer table, of course, the tenant ID and the customer ID. So let's go run this, right? And you'll notice that it fails. And the reason it fails is because one of my tables is distributed on tenant ID and one is distributed on customer ID. And so the system doesn't permit you to effectively create an arbitrary foreign key between the nodes. And really you don't want it to, because when you move into distributed systems, you introduce latency of the nodes connecting over the network. And if you think about the level of throughput that these systems are typically supporting, to check the foreign key across nodes, effectively in this scenario, you'd need to check it across the entire cluster, will introduce a lot of latency. And so by design, we enforce that if you're going to create a foreign key, the system needs to be able to guarantee that the primary and foreign key relationship will exist, or foreign key relationship will exist only within the node. Now, it will inherently exist in each node locally, but not across nodes. And so how do we get around this, right? Because this is on tenant ID, so we know that all records for a given tenant ID will be on the same node. But remember up here, this was on customer ID. And customer ID could span multiple tenants, and so you could have a problem there. Now, the system doesn't sort of understand how to handle that. And so what we can do here is, our foreign key failed here. Let's take a look at our Citus view again here. And you can see the problem as I just described. Customer ID and tenant ID are my two keys. I need a common key, a common distribution key to create this relationship. So we've got this alter distributed table function. We used it up here, remember, as well, for changing the shard count, but it can take some different parameters depending on what you want to do. I'd like it to go back and change my customer table. And rather than being distributed on customer ID as it is at the moment, I'd like it to be distributed now on tenant ID. So I'll go and select that and run this query, and that'll run. And if I run Citus tables again, now both of my tables are commonly distributed on tenant ID. We absolutely know that all values of tenant 1 on both tables are guaranteed to be stored locally. They're co-located on the node. And so if I go ahead and run that foreign key query again, this time it succeeds. The Citus engine has the smarts to understand that it can guarantee to enforce this relationship on each node locally. And so now we've got a strict relationship between two tables. So let's keep going. I want to create the inventory table now as well. So we've got a tenant ID again. That's common because it's a multi-tenant app. So every table has the tenant ID in it. We've got the inventory ID. You can think about this as like a stock keeping unit. And then we've got the item name as well. We just gave it a varchar 50. Primary key, tenant ID, inventory ID that I'm abbreviating, and you can see the columns. So let's go ahead and run that. So we've got the inventory table now as well, and we'll want to distribute that, of course. So we learned our lesson not to use anything other than the tenant ID. So we'll go ahead and use tenant ID right there. And we'll check what we've got. And as you can see, we've got 3 tables, all commonly distributed on the tenant ID. And we can actually go and now put the foreign key in place as well, which is going to be from effectively the inventory table down to the sales transaction table as well. So we'll go and create this key, and this will work. And so let's stop for a second and just recap what we've actually gone and done here. So we've got the customer table, and what we've done is we've distributed that on the tenant ID. Let's write that in full. And we've got a foreign key from the customer table to, let's use something like that so it looks a little different, to the sales transaction table, right? On the common keys, which was, I think it was tenant ID and customer ID, right? And that's going to the other table, which is tenant ID and customer ID. Okay. Now, sales transaction was also distributed on tenant ID. It doesn't have any foreign keys hanging off it, so we don't need to add that. And then sales inventory, we also distributed that on the tenant ID, and we gave it a foreign key, and that was, as I recall, from the, well, of course, from inventory to stock transactions, and that was on the tenant ID and the inventory ID going there as well. So we've got two foreign keys here between three tables. Let's just finish this for completeness. I think that's right. And that's what we've basically gone and done now. Okay, so now we need to start playing with some data. So let's start by inserting into the customer table. We'll take the tenant ID, customer ID, first and last name. And we've got a couple of things here. So two customers in the first tenant, one customer in the second tenant, and then customer one and customer two. Obviously, these pairings need to be unique to honor the primary key unique constraint. So we'll go and insert those values, and then we can insert into inventory. Of course, we need to insert into inventory first because that's upstream of the sales transactions. If we try to put anything into sales transactions without the associated keys in inventory, that will obviously fail by design, which means the database is doing its job. So we'll go run that. That's great. And now what we'll actually go do is insert into sales transactions a tenant ID, customer ID, transaction ID, inventory, the time, and the amount. So let's go run that. Okay, perfect. So now we've got everything. So now thinking back to what we did before in demo 1, where we showed how the Citus engine will automatically collocate and execute a query on only one node where it trusts and understands the sharding strategy. So let's take a look here. I'm going to select start from customer where tenant ID equals 1. By the way, we can cheat. We know the answer already. It's going to be Fred Smith and Sally Jones because that's tenant ID 1. So let's just check that. We'll run the query. And sure enough, there they are. But more importantly, if you think back to demo 1 and the scalability of only using the compute node where the data resides, because we're sharded, our shard key is the tenant ID, then if I run the explain plan, that little task count that we pointed to before is of course is only 1. We've been able to hit only a single shard on a single worker node. In this case, the other worker node has done no work, no computational work at all. So again, you start to think of a busy multi-tenant app. Really, the cluster becomes very efficient at scaling as a given tenant's queries are only handled on one node. You can imagine how you could scale out to dozens of nodes and effectively enjoy near linear scalability in these multi-tenant apps as you scale the application. Let's now do something different. Let's go and say I want to select star from the customer table where the customer ID equals 1. So there's no tenant ID here. This is great, and this is one of the beauties of Citus, is that it understands how to do a fan out query. And so here I've actually returned two different tenants here, which probably is not what you want the app to do, but as a developer, if you want to be able to run analytics across the totality of the tenant customer base, this is pretty handy. And so we're going to explain that. Remember, we set it to 64 shards before. Now, the system is smart, but it doesn't know, of course, that there's only data in 2 shards. And so it knows that it can't isolate the query to a single shard because there's no equality predicate on the tenant ID. So it just needs to hit all 64 of them, and that's what it goes and does here. So let's do something a little bit more fancy. Now we're starting to get into some joins. Right now, joins can be a little more tricky. Let's just move this down a little bit because sometimes you need to move data. So let's go and run this. You can probably see where I'm going with this one because I'm joining on I'm filtering on the tenant ID, but critically, I'm also joining on the tenant ID. Right, and so now the system understands that I only want tenants where customer tenant equals Sales transactions tenant should be ST, I guess, not SA. Call it sales, I guess, SA. But the tenant ID equals 1. So let's go run this query. This will come back, remember Sally and Fred in tenant 1 and a sum of their sales. But let's go and explain that. And as we would expect, task count 1. So the point is the scalability to be able to run these queries locally only on a single node is not sort of limited to trivially simple, select stars with a filter. You can start to build very complex queries. I could expand upon this with all sorts of windowing functions and aggregates and averages and all sorts of stuff. So long as that join and filter are on tenant 1, that workload is going to be sent down to that query. Now, if you think about the compatibility I talked about with Postgres extensions and everything else, you imagine that we're starting to leverage things like HLL and other things for approximate count distincts and that big ecosystem of extensions where they can be applied to this query. Again, so long as the tenant's 1, we're going to push that work down to a single node. And so the scalability of the platform is pretty awesome. Now, of course, if I take that away and we go run the query again, we effectively get a multi-tenant query, bills here as well. And obviously, if we go and hit the explain, there's the 64 that we would expect. So this is the end of this demo, and you can see basically just a more detailed and slightly slower paced end-to-end about starting to build these applications in a really scalable manner on the platform, where you can build multi-tenant apps, localize that workload to each node, and that's going to enable massive concurrency and scalability and efficiency as you scale out that cluster, the application grows. And we also showed how you can grow the data by adding shard counts to make that data into more smaller chunks that can be attached to a larger number of nodes. Let's switch over back and start to wrap up the session. Okay, so that wraps up the second demo, and you can see how we can start to build these really scalable applications using Hyperscale Citus. We covered a lot in this session. We started with effectively how distributed tables work, explained the basics of the Citus extension and using those functions for, first of all, creating Postgres tables and then creating distributed tables and reference tables and how that works, how they balance across the nodes, how they can be rebalanced as well. And we walked through all of that effectively in that demo. We then talked about the benefits of scalability. We talked about, remember, the latency of effectively how latency can be reduced and performance can be increased beyond linear improvement by moving from a single node to scale out system. And we talked about that example where we were able to achieve 13x throughput improvement versus only a 5% increase in cost. You're remembering how we talked about how database systems can occasionally fall off a cliff once cache hit ratios start to drop and IOPS start to impede the throughput of the system. We talked a little bit about how we build on open source Postgres and our ability to deliver the latest version of open source Postgres within 24 hours effectively of when the community ships it, but we're shipping it in the managed service to enable developers to have the latest capabilities from Postgres effectively on day one. And then that came, of course, with extensive support for extensions as well. We talked about some of the core capabilities in the managed service, the ability to do online scaling out of the cluster and the rebalancing of that data, rebalancing of data both when the cluster scales, but also rebalancing of data on a fixed size cluster if the workload has become imbalanced and creating hotspots and you want to actually move shards around between nodes. We covered high availability, read replicas both in the region and cross region, and gave a really quick walkthrough in the portal on how you can enable some of those capabilities. And then finally, we just closed with the demo that I just showed. Thank you for joining the session today. I hope it was informative to give you both a bit of an overview on how to get started with the service, but then some of the code-based examples on how to start building and really building scalable applications with the service. I've got a couple of other slides to show just quickly with respect to Microsoft and the support they provide to the conference, of course, and then a couple of prizes, I think, as well. So thank you again for joining the session.